Okay, so we're moving on with constant acceleration, and we're going to introduce some of the constant acceleration formulae in this lesson. So we've looked at displacement and displacement time graphs, and we've worked with displacement as a vector. We've looked at velocity and velocity time graphs, and we've worked with velocity as a vector. We're going to try and extend that, and we want to start generalizing to work with these variables under a very specific condition of constant acceleration. Now, using what we know so far, I'm going to show you how to derive two of these equations, and then we're going to work on some problems involving those. And in the next video, the next lesson, we'll look at how to derive the other three. What's nice is these derivations do come from a velocity time graph, something we're already familiar with. How can that turn into useful equations? Now, you may have come across these before. These are colloquially known as the Suvat equations. More technically, they are kinematic equations, the old school term for the study of the motion of objects. I actually want you to refer to these as the constant acceleration formulae. They can only be used when we have constant acceleration. If we're using them, we know we have constant acceleration. If we know we have constant acceleration, we have license to use them. So I will continue to refer to them as constant acceleration formulae. Okay, let's reintroduce our velocity time graph. Now, if an object is traveling and it is increasing its velocity at a steady rate, we can say that it has constant acceleration. This is an assumption. In real life, it's very hard to make your acceleration constant, but we generalize, we model the situation as having constant acceleration so that we can make use of some of the mathematical tools at our disposal, including the constant acceleration formulae that we're going to look at. So in this generalized model of my journey, I've increased my velocity. In previous lessons, we've seen that the gradient of a velocity time graph represents the acceleration, which is, in all cases, the gradient is the change in the vertical axis or the vertical variable divided by the change in the horizontal axis, the horizontal variable. So the change in y over the change in x. Now here, my vertical axis is velocity. So I somehow want to define these 2 points. My final velocity, I'm going to call v. This is final velocity or current velocity, velocity later on in the journey, lots of ways to talk about it. The final velocity versus the initial velocity. So v and u are the notation we'll use for these two different velocities. Okay, back to the formula. So the gradient, the change in velocity, so final velocity being v, initial velocity being u, the change is v subtract u. The change in time, well, let's call this value here t, so an unknown value of time, and the initial time was 0. So t minus 0, that's just t. The change in velocities, v minus u, the change in time, t minus 0. Acceleration must equal v minus u over t. Okay, this isn't quite the most usable form. We're going to rearrange and we're trying to make v the subject. So multiply across by t, we're going to add u to both sides, and here we have it, v is the subject. V equals u plus at. Now that's one of our 5 constant acceleration Suvat equations. And this was derived from the gradient of a velocity time graph. Another feature of the velocity time graph that we've seen in our previous lesson is the displacement. How far have we traveled as a vector? Well, we know that we can find the displacement of a velocity time graph by finding the area underneath the curve, the area underneath the graph, the area in between the graph and the horizontal axis. Well, we can use geometry, and I hope you can all see the trapezium that we have in front of us. You're welcome to split this into a rectangle and a triangle, but I do think we need to make use of the trapezium area formula as much as we can as we make our way through these type of questions. Okay, so I'm going to use the trapezium formula. A and B must be the parallel sides, these two vertical lengths. One of them has a height of u and the other has a height of v. So we've got u plus v divided by 2. And now the height, or the distance between the parallel lengths, is t. So here's the second of our constant acceleration formulae. Now both of them had their origins. They've been derived from a velocity time graph. Now a typical constant acceleration question will give you a scenario and ask you to make use of these formulae. But every once in a while, you are asked to derive from first principles, so from scratch, from a velocity time graph, can you derive these two formulae? So I want you to be prepared and to practice these derivations so that you're ready if you're assessed specifically on them. Okay, so I just want to make the point that these formulae are actually given to you in the formula booklet. But historically, students practice enough, practice so much that these formulae are ingrained in their memory. They know them because they've engaged with them so often. I wouldn't really want you going into your final exam still unsure of your SUVAT formulae. There's so many other formulas to worry about. SUVAT should not really stop us or block us from the flow of our work in the classroom nor the exam hall. Okay, let's see this in action. So we'll start with an example where we're asked to calculate the final velocity of a car that accelerates at 2 meters per second squared from an initial velocity of 3 meters per second for 5 seconds. All right, as soon as I know it's a constant acceleration question, I'm going to collect or get ready to collect my SUVAT variables down the left-hand side. I'm going to produce a diagram to depict what's happening in this journey segment. We had an initial velocity of 3 meters per second. The journey lasted for 5 seconds. I do not know the velocity at the end of this journey segment. What I do know is that it's accelerating 2 meters per second squared. So I'm expecting this number, this answer, to be larger than 3. Okay, now the actual object starts here and it's going to move to the right. It's going to continue moving to the right for the whole of its journey since it's accelerating. Okay, let's collect our SUVAT variables. The initial displacement we do not know. The initial velocity is 3. The final velocity we don't know, but we're looking for. So I've boxed off that question mark. The acceleration we've been told is 2, and the time for this journey is 5 seconds. Okay, and quickly, let's just denote the positive direction on our diagram. It's moving to the right. Now we need to choose which of these formulae we should use. I want a formula that makes use of my known values and the one that I'm trying to find. So a formula that uses U, V, A, and T. And that's the top one, right here. So now that we've chosen, we need to make sure that we quote the formula. The examiner has a mark scheme that says they can give you a mark merely for showing the intention to use the correct formula. So you quoting it at the first instance gets you the mark, whether you put the numbers in or not. Always quote the formula. Apart from that, it makes it very clear what calculation you're doing rather than starting off with substituted values. You should be doing your best to communicate your maths extremely well in a written form. Quote the formula. Then we'll substitute in. So we're looking for V. 3 is our U value, 2 is our acceleration, 5 is our time, and we simply evaluate that to get velocity of 13 meters per second. This makes sense. I was expecting a larger velocity, a higher magnitude velocity than 3, and 13 fits the bill. Okay, let's try another one. This time, we've been asked to calculate the time taken for a car to accelerate uniformly from 4 meters per second to 16 meters per second over a distance of 30 meters. Okay, as always, as soon as we know it's a constant acceleration question, we list our SUVAT in a column. We'll come back to that. We're going to try and get a visual to see exactly what's happening. Initial velocity was 4. The velocity later on, or the final velocity, 16. And we know that the distance covered was 30 meters. Okay, positive direction is off to the right. If the object started here, it's moving in this direction. Let's collect those SUVAT variables and see which formula to use. Displacement of 30, initial of 4, final of 16, unknown acceleration, unknown time, but we're looking for time. We need a formula that uses S, U, V, and T. And that's the second formula over here. Once again, we're going to quote the formula. This is good exam technique. Quote the formula, substitute the values in, rearrange and evaluate. We don't even really need a calculator here. This bracket evaluates to 10, dividing by 10 gets us a time of 3 seconds. It would take 3 seconds for an object to accelerate from 4 meters per second to 16 meters per second if it had 30 meters in which to do so. On to the next one. Here we're told a tennis ball is struck, and after 5 seconds, this ball is traveling at a velocity of 14 meters per second. We're told that the ball decelerates uniformly at 4 meters per second squared. We're asked to calculate the velocity of the ball immediately after it was struck. As always, a column of Suvat. Let's put this diagram together and be really careful to read exactly what's being told. A tennis ball is struck. After 5 seconds, it is traveling at a velocity of 14 meters per second. That's a new velocity. It's not the initial velocity. That's the velocity after 5 seconds. That's the velocity later on. This is the 14 meters per second. The initial velocity we don't currently know. What we do know is that this object is decelerating. Now, technically, if an object is decelerating, its velocity will keep reducing until it gets to a velocity of 0. And after that, it will have a negative velocity. So technically, objects can double back on themselves. If your velocity becomes negative, you start traveling in the opposite direction. We won't actually have that in this case because we have context. We're told it's a tennis ball, and we know enough about a tennis ball that when you hit it in one direction, it would keep on moving in that same direction. I just want you to be on the lookout for situations where deceleration is involved and know that it might actually need to be modeled like this. Our context in this case lets us know it's a tennis ball and it won't be changing its direction. Okay, just to finish off the diagram, unknown initial velocity, and this is our positive direction. Okay, let's collect the Suvat variables. Displacement, unknown. Initial velocity, unknown, but we're looking for it. Final velocity of 14. Acceleration is -4. Time is 5. Which formula do we use? U, V, A, and T appear right over here in this formula. Okay, as always, quote the formula, substitute your values in, and some sensible rearranging. You probably don't need a calculator for this one either. U is going to equal 34. The initial velocity, 34 meters per second. That makes sense in this scenario. We knew it was decelerating, so it had to start with a higher velocity than 14. And as you do more and more questions, you'll get used to what sort of values we should get with an acceleration of 4 or -4 over a 5-second period. There should be a velocity change of 4 times 5 of 20 units. So you'll get a feel for when your answers are coming correct. And just one more example. Here, we're told that a particle starts at 48 meters per second and moves along the x-axis from the origin to a point A in 4 seconds. Okay, here's my diagram. I'm starting from the origin and I'm moving to a point A. I'm just going to label arbitrarily, A is here. This journey segment took 4 seconds. The initial velocity, 48 meters per second. And our positive direction is off here towards the right. Okay, we're told, or we're given, that the particle decelerates uniformly at 3 meters per second squared. Find the velocity of the ball at point A. All right, so small journey segment here. We have an unknown final velocity. That's what we're looking for. Let's collect our Suvat variables. We have no information about the displacement. The initial velocity is 48. The final velocity we're looking for, acceleration of -3 and a time frame of 4 seconds. Okay, we're working with U, V, A, and T. You're getting used to this now. Which formula? It's V equals U plus AT. Quote the formula, substitute the values, rearrange, and we're trying to evaluate for V. Okay, so no rearranging needed. V equals 36 meters per second. That's the velocity when it gets to point A. Okay, we're then told at point A, the particle is subject to a new acceleration. We are working with constant acceleration formulae. We can only use these formulae in a journey segment where the acceleration is constant. At A, the acceleration is going to change. We cannot use information from the first part of the journey, the 4 seconds, the 48 meters per second, to now refer to the second part of this journey. We can, however, use the point A and anything that's happening at A. We found that the velocity was 36 at A. We will be able to use that. Okay, continue reading. We'll see the object comes to rest at point B, which is 46 meters away. Okay, we're going to extend the diagram. 46 meters away. Coming to rest means the velocity becomes 0. Rest means it's stationary. It's not moving. It has no velocity. Velocity equals 0. Okay, like I said, we can use information about point A. We found that the velocity at point A is going to be 36. So I'll add this to the diagram, 36. And this is the linking point between the first journey segment and the second journey segment. Okay, so collecting the Suvat variables for the journey segment A to B. We know the displacement to be 46, the initial velocity to be 36, the final velocity to be 0, and we have an unknown acceleration. We don't need to find it. We're just told in the question it's a new acceleration, so we can't use -3. But we're looking for the time that this journey segment is going to take. Okay, we're working with S, U, V, and T. This is the second formula over here. This is the second formula over here. Okay, so as always, we're going to quote the formula, we're going to substitute the values in, and we're going to rearrange to make T the subject. Now, just looking at the numbers, you probably do need your calculator for this one. 46 divided by 18 gets us 2.56 seconds. So that's the time for this journey segment A to B. In this question, we had to be really careful in our reading. We set up one journey, but it was not constant acceleration all the way across. 2 different journey segments, origin to A, and then A to B. Okay, so I'll leave you to get on some practice now and to get a chance to see this in action in a number of differing scenarios.